I'm going to read this guy's name because it's obvious.
Okay, it's quiet.
Ready?
Yes.
Welcome, everyone, to Astronomy State of the Art. This is one of our live sessions, open for all your questions on everything from comets to cosmology. Oh, I just got closer, or I just grew. So, happy to take your questions.
Yep. First question is regarding the James Webb Telescope. What are the advantages of having a telescope so far from Earth as opposed to an Earth orbit like Hubble, where maintenance and repair missions are possible?
Oh, great question, because the thing that is freaking out the James, they would never admit this in public, of course, but the thing that freaks out the James Webb technical staff, engineers, and mission managers is the fact that it's not serviceable, the fact that it's going to be 1 million miles from the Earth, no astronauts to fix it like they've done the Hubble 5 times in 25 years. So you got to have a good reason for doing that. And basically the good reason is that the Hubble Space Telescope is not in the optimal orbit for a telescope. It's not the best place. Low Earth orbit, which is between sort of 200 and 350 miles above the Earth. I mean, that's, you could drive that distance straight up in an afternoon if you had a car that could go straight up. It's not that far. Is not a pristine space environment. You're definitely above 99.99% of the atmosphere, but there's significant air glow from below you, from the atmosphere, and the atmosphere, of course, is not far below the telescope. You pass through radiation anomalies, the famous South Atlantic anomaly, which the Hubble Space Telescope passes through in its orbit, basically renders about 15 minutes of each 90-minute orbit not useful for scientific data. So you lose some right there. The efficiency of the telescope is compromised. Also, as you're probably aware, the near-Earth orbit environment is getting cluttered with debris, space debris, junk, pieces of satellites, missions that have fallen apart, small rocks in the orbit, and so there's a significant chance of collisions and damage. And the Hubble has taken some collisions, nothing catastrophic, nothing bigger than the head of a pin, but the solar arrays on Hubble show clear evidence of micrometeorite or debris damage, going, of course, at very high velocities. So there's extra radiation, there's extra particles and damage. There's the Earth below you shining brightly, which is limiting your view of the sky. So all of those reasons mean that if you go to a Lagrange point 1 million miles from the Earth, which is a sort of, it's not a fully stable gravitational situation, but it's what they call quasi-stable, so very small amounts of fuel can just keep you in position. You have a much more pristine environment. It's truly dark, completely dark. The Earth is not really an issue. The sun can easily be avoided. And so you have much more flexibility of scheduling, of programming the telescope, and the stability of the data and the reliability of the data is very high. Now, James Webb was just built with one suite of instruments that were designed to last the entire mission, so there was never any intention of upgrading the instruments. So it being not serviceable is not an issue there. I think the biggest concern with James Webb is the deployment phase, because the James Webb is a 6.5-meter telescope, but it's folding itself into a much smaller capsule to be launched, and it will unfold those mirrors like flower petals in orbit, also deploying solar arrays and unfolding them, and struts and spars and all sorts of moving pieces. I think there's something like close to 100 moving mechanical parts in the James Webb telescope structure. And that gives engineers slight nightmares, especially the unfolding of the optical telescope assembly, because if that doesn't work, then there's really a limit to what can be done. It's exhaustively tested on the ground, of course, before launch, which means basically now it's being tested. But that is probably the biggest wild card about the James Webb, which has passed so far all of its technical tests. So there's no shadow over the project. The shadow over the project is a price one, as it exceeds $8 billion. But the technical parts have been so far under control, and the instruments are past their ground tests. The telescope assembly has passed its ground test. The mirrors are all within spec. So the project is, full steam ahead.
Next question is from Ryan. Who do you think will get to Mars first, the private space industry or the government? Who do you think will lead the future of space exploration?
Good question, big question. So as you've probably seen, we'll do the private part first. Mars One, led by a man called, I think it's Blas Landorp, a Dutchman, private company. He's a wealthy philanthropist. He has some other deep pockets behind him. Mars One has taken their first intake of proto-Mars astronauts down from, I think, 116,000 to just over 1,000. And those 1,000 actually undergo significant pre-training before filtering down to 100 and then probably to the more likely number that will actually go. You know, the conventional wisdom on the Mars One project oscillates between, well, they're ambitious, but they have a chance, to completely overblown hype and they'll never do it. Obviously, there's some, I talked to NASA engineers, and there's some prejudice on NASA engineers' part to believe that they don't know what they're doing. They do have good technical people on the project. As you probably know, it's a one-way mission to Mars. Makes it cheaper if you don't have to bring people back. So these are people willing to give their lives for this mission. And they're not all old people that have applied. I mean, a lot of younger people have applied, knowing that they would be part of a colony never to return. The goal is to land, I think, 2 people a year and just gradually build a colony. They obviously have to do some advanced legwork, which involves setting up a sustainable small habitat on Mars and shielding it from the cosmic rays and meteorite impacts that are quite frequent with such a thin atmosphere. The technology to do that is not very sophisticated, it's well known, but it is a matter of delivering quite a lot of material to Mars. So there's probably 4 or 5 supply missions that would precede any potential colonist. They're holding what I think almost everyone agrees is a completely unrealistic timeline on this, of imagining that the first colonist might put down in 2022. I don't think anyone really knows that. So can they do it, and is their timescale reasonable? They might be able to do it, but probably not that timescale, talking about more like the late 2020s. So they're the leading private sector company. Now Space Adventures, which is the parent company that hosted, was the parent company for the 7 space tourists so far, those people that paid $15 to $20 million for a joyride using Russian technology up to the space station. Space Adventures, which has Peter Diamandis on its board, and he's the founder of the X Prize, so he's a pretty serious space entrepreneur. Space Adventures also has a Mars mission in the offing. Not so much released about that publicly, about how they're going to do it. They'll be using They'll be using Russian technology. So they're going to use, they're going to adapt Russian launch facilities, Russian Earth orbital facilities, and then turn them into Martian orbital facilities and Martian landers. So the Russians do actually have the hardware to do this, and Space Adventures is just going to co-opt it for a different purpose. They're fuzzy on their timeline too, but it's got to be the late 2020s. So those are the 2 main private sector players. Space Adventures, you know, has significant street cred, and you can understand part of that's just because they are in tight with the Russians, who really badly need the money for their space program, and the Russian hardware is fairly primitive. You know, the Russian Proton rocket is unchanged from the early 1960s, but it's also pretty reliable. So they have the heavy lift capability. The Russians obviously had their own orbiting space station, Salyut, and so they know about long duration missions in space. So I think they do actually have a chance to succeed. NASA's plans are completely up in the air. Again, the technology exists to set up a Martian base. All you need to do is use I say all, but it's expensive and it takes a while, is mine the Martian regolith for oxygen and water. If you can do that, and the rock contains plenty of trapped water under the ground, especially if you went to a near polar region, and plenty of oxygen that you can liberate with modest amounts of energy. So with oxygen and water, you have the ingredients to set up a base. Oxygen is also useful because it's a major component of rocket fuel that you would need to resupply the base and get people off and on. So the American plans, or NASA's plans, are going to be slow because Martian sample return is not going to take place until about 2022 at the earliest, which is when Mars 1 says they're actually going to put people on Mars, although we don't believe on that time scale. So humans to Mars in NASA's plan is pushed back well into the 2020s, probably 2030 or beyond. And that's because there's no money. The cost of such a mission, nobody really knows how to estimate it, but it's between $50 and $100 billion. And that's not for a permanent colony. That's for setting up a base and occupying it for a while and then bringing people home. And NASA just doesn't have that much energy in its budget to take on something large like that. So really, it's pretty much, therefore, I believe, although the government projects could and should get there first because they do have deeper pockets, the way the space agencies are funded, it is indeed possible that the private sector will get there first. And if I were going to bet, I think that's where I'd place my bet. I'd actually put my bet on Space Adventures.
Next question is from Stan. In your book, How Will It End? You support the Big Freeze end to the universe. Could you comment on the other theories such as the Big Rip, Big Crunch, or cosmic inversion?
Wow, cosmic inversion. I'm going to have to go and look that one up, so I don't know that one. Big Crunch is the sort of oscillating universe theory that was popular sort of in the 50s, 60s, and 70s before we made detailed measurements of the amount of dark matter and normal matter in the universe, and before we discovered dark energy. So the Big Crunch is just a mirror image of the expansion from the Big Bang, where the universe reaches a maximum size and then recollapses to another singularity, another Big Bang, sort of high density state. And that's got a nice symmetry to it. It's a sort of elegant idea. It was actually attacked theoretically before it was probably disproven observationally. Stephen Hawking made interesting arguments that if the universe went through an oscillation of Big Bang, Big Crunch, Big Bang, Big Crunch, the entropy, the total entropy of the universe would increase through the oscillations. And that logically, since you don't know when this process started, the entropy of the universe would gradually reach a super high or sort of untenable level where everything was chaos and uniform structure. So Hawking argued on almost purely theoretical grounds that the Big Crunch was unlikely to be the case. Since the late 1970s and early 80s, when we measured the mass content of the universe, it's been clear that the dark matter and normal matter put together only amount to less than a third, roughly a quarter, of the mass needed to close the universe, or for the universe to reach a maximum size and potentially recollapse. So we fall short by a factor of 4, which means that observationally it's extremely likely that the universe will expand forever. Dark energy only accentuates that conclusion because dark energy is a component of the universe that is making the expansion accelerate, making it even less likely that it's going to recollapse. Which leads us to the Big Freeze, and the Big Freeze is the logical endpoint of an ever-expanding universe. In about 500 billion years or so, give or take a few, who's counting, all the stars in our galaxy and all galaxies will burn out. Everything will turn into white dwarfs, black holes, neutron stars. That happens fairly quickly. The white dwarfs for the low-mass stars will take a while. That's what takes the hundreds of billions of years. But eventually all the stars will die. And so the fusion energy in the universe, in all galaxies, ours and all the others, will end. Galaxies will go dark. And in that sense, and because the universe is expanding and so space is getting ever more empty and ever colder. Remember, space is now at a temperature of 3 degrees Kelvin, which is still pretty darn cold, but it's not 0. As space expands, every factor of 10, that temperature goes down a factor of 10, and so eventually space will get very close to absolute 0. So space itself, the radiation that fills space, will extend to ever longer wavelengths, long wavelengths, radio waves, meter-length waves, radio waves tens or hundreds of meters long, and then all the energy sources in the universe will die out, and in that sense, the universe faces a Big Freeze. The last option mentioned was Big Rip. So Big Rip is a variant of dark energy, where if dark energy has a particular property, it leads to an a crescendo, basically an exponentially expanding rate of space-time pulling itself apart. Because dark energy, we believe, emerged from space-time itself. It's not some external force or some pulling from another dimension or region. It's space-time itself ever faster expanding. And in the Big Rip scenario, that ever faster expansion of space-time eventually propagates down to the level of structures in the universe, which means that at some point it propagates down to galaxies, and galaxies are ripped apart. Stars that are held by the gravity internally of the galaxy will no longer be held together because the space-time is expanding fast enough to pull the stars apart, so galaxies sort of evaporate, and then eventually, in a crescendo, in an accelerating crescendo, that pulling apart propagates to the level of stars, so stars rip apart, and obviously planets that orbit stars will be pulled away from their orbits. And then on an even shorter time scale, it propagates all the way down to objects like us, and eventually atoms. And since atoms exist in space-time, if space-time is pulled apart on the scale of atoms, then matter itself would disintegrate. So in a nutshell, that's the Big Rip concept. Big Rip would only happen if dark energy has a particular property that it has not been observed to have so far. We know very little about dark energy, but the figure of merit beyond its actual existence is called its equation of state. That's a sort of physics term for how the pressure of the dark energy behaves relative to its energy density. And it doesn't seem to have that values that accords to the Big Rip theory. So we haven't definitively ruled out Big Rip, but it seems very unlikely to be the case. So we're faced with big freeze, but a very long time. It's nothing loosely focused.
Next question is from Benjamin Stanley. Do you think something like asteroid mining is potentially profitable or even viable?
Yeah, it's a good question. I don't think we talked about it at all in our course. It's on the table as a practical use of space. People are often wondering what's the point of the space program? Why do we want to go back to the moon? Why do we care about exploring the outer solar system? These things don't have any practical importance. Well, when it comes to resources, we are actually exhausting some of the resources of the Earth that we have ready access to. We're not running out of aluminum or anything like that that's fairly abundant in the crust, but we are running out of obviously rare earths. You've probably heard about that, the Chinese have cornered the market in some rare earths that they mine and are not found anywhere else, and those elements are vital in manufacturing processes, and those ingredients are now very expensive, and there's obviously metals, platinum. It's a good example that's used in many industrial processes, and that's also become quite expensive due to scarcity. So people have done the math, and they figured out that a sort of moderate-sized asteroid, by moderate, remember the biggest asteroid is 1,000 kilometers, so a pretty small asteroid of maybe 10 to 15 kilometers in diameter, would, if you just took it at book value based on the value of rare earths and precious minerals on the Earth, have a value of a couple of trillion dollars, sort of like the GDP of the United States. That's a phenomenal amount of money. That is a very raw number. I mean, it's an accurate number based on supply and demand on the Earth. So there are two huge issues, and the first is, what does it cost to bring an asteroid into Earth orbit and harness it, and then mine and deliver those materials in a sustainable way, sort of on an industrial scale down to the Earth. And the costing of that enterprise is extremely precarious. I mean, it's very primitive costing. There would, if you're just lucky, if you're fortuitous, there are going to be near-Earth asteroids whose orbits bring them close enough to the Earth that quite a modest adjustment of their orbits could bring them into Earth orbit. And NASA's, of course, been looking at that quite seriously because they have an asteroid capture mission that's under consideration. They're not planning to do the mining. They just want to capture a very small asteroid just to see that it's done. So you could probably get the asteroid, if you're lucky, into Earth orbit for not too much money. But mining and refining and delivering the materials down to Earth without something like a space elevator, which we don't have yet, is probably extremely expensive. And so the economics of the mining start to look a bit precarious. But the other obvious thing is that once you've cornered the market in these particular rare ingredients, you've altered the supply and demand curve. As those older people with long memories might remember, the Hunt brothers who tried to corner the market in silver, I think in the early 1970s, and the bottom dropped out of the price of silver, and they lost a ton of money. So of course, when you create an abundance of new supply, you alter the cost curve, and possibly the investment that was required to bring that to the Earth is no longer worthwhile. And I think economists have been fairly skeptical that asteroid mining is a viable economic enterprise. The only, extra thing I would say that is in its pioneering phase, that's likely to be true of everything. Commercial flight and space flight, all of these things were very expensive, required extra investment before they became viable commercial operations. I could foresee, flash forward 50, 60, 70 years from now, where mining materials on the moon or asteroids, gets through its teething phase and reaches industrial scales, where it just becomes the way we get our mineral resources. But to get from A to B is really tricky, because you have to be willing to invest a huge amount of money and potentially lose it all if you're one of the pioneers.
Okay, the next question is from a student on our Udemy class. What are falling stars? Are they dying stars?
So falling stars, there are different terms for this. Generally, people consider that term the same as shooting stars, or just when you see a moving light in the sky that is not, for instance, a satellite. So satellites do track across the sky, but they're steady. They don't change in their brightness, and you can follow them entirely across the sky. If you look towards the south and have a little web app going, you can find out where the space station travels, and that's quite easy to see by the naked eye. Shooting stars seem to be stars, and of course that's what people thought they were. It turns out that all of those things that you can see, and if you go out on a dark sky at just any time of the year, go out when the moon's not up, of course, because it bleaches out your ability to see these objects, you're going to see a couple a minute, actually, if you go to a truly dark sky. And they fluctuate in frequency, and you might have a period of time in a minute where you see 6 or 10. And they're quite impressive. It turns out that virtually all of those events are microscopic, really microscopic, grain of sand-sized rocks or smaller, traveling at tens of thousands of miles an hour up to 100 or so 1,000 miles per hour, which is how fast some space debris is moving, just burning up in the upper atmosphere, 40 to 80,000 feet above your head. So it's kind of remarkable that a light visible to your eye that looks like a star, looks like something big that's burning up in the sky, is actually caused by something really tiny, almost too small to see, that's burning up, miles and miles above your head. And that energy, the energy release, the kinetic energy of something traveling at that speed, it's a half mv squared, so it's a tiny mass, but v squared is extremely high. That kinetic energy turned into heat does make quite a lot of light for a very short time until the thing just evaporates. And that's what essentially all shooting stars are. Now occasionally, and this kind of thing gets into the paper, and you can see videos about it on YouTube and elsewhere, occasionally a shooting star is a really substantial piece of space debris. But it's still very unlikely to be larger than about fist size or potato size. So the Chelyabinsk object in Russia from a year or so ago, and other sort of high altitude breakups of substantial material, they happen, every few years, maybe every decade. That's pretty rare. The things you see every night are really tiny. Oh yeah, and I'm reminding people, if you have questions, to post them on Google Plus now.
Our next question is, some very young stars have jets. Explain, please, what are the nature and origins of star jets?
Yeah, that's a good question. I've never had that question or one similar. Young stars are hard to diagnose what's going on because they occur, star birth and the early phases of a star's life occur in places shrouded by gas and dust. So just take the Orion Nebula as an example. You can see that. It's a naked eye object and really impressive with binoculars or a small telescope. That, and you can see embedded stars, young stars, but most of the action is really hard to see because when stars form, it's chaotically a number of stars forming in one extended region, and the gas and especially the dust obscures optical light. Essentially, optical light can't get out of these regions, and therefore we can't see into them. So it's taken a while for people to unravel what happens when stars form. But it does seem that there's a period of a star's life. First of all, the early phase of a star is somewhat unstable. It takes a while to settle down into the stable form, say, of the sun in its early life. And the sun, in fact, had an unstable phase early in its life. There's also a phase where the star has formed. There's a self-gravitating object with fusion occurring at the center, but the material from which it formed is not yet driven away or exhausted. So the disk out of which the star and its attendant planets have formed is still present, or the residue of it is still present. Stars are also rotating. In the conservation of angular momentum, when that big, slightly rotating gas cloud collapsed to form a star and planets, the rotation is amplified. So young stars are rotating, and they're still surrounded by a debris disk or residue disk. And they're emitting a lot of energy. So they're highly luminous compared to the sun, maybe 10 to 100 times more luminous than the sun at the very earliest stages of their life. All of those three conditions go together to make a possibility for jets, because it means that the energy leaving the sun can entrain material that's in the equator, in the disk, and then shoot it up the axis, up the rotation axis of the star, to not quite relativistic, but very fast speeds where that material will, of course, glow. It will radiate. And so stellar jets appear to be phenomena that are transient. They only occur for a short period in a star's life. How short? Maybe a few tens of millions of years. And now with high spatial resolution imaging, like Hubble Space Telescope, we've actually observed these jets. So young stellar jets have been observed with Hubble, and also with Spitzer, because Spitzer can see through the dust in the infrared, and actually the jets really pop out sometimes if you observe them in the infrared. So it's not clear if every young star has a jet phase and makes jets, and sometimes the jets are not symmetric. Sometimes there are one-sided jets, maybe because the material, the debris in the disk was lopsided or asymmetric, and sometimes they're two-sided, and then there are clearly very young stars that don't have jets at all. So it's not a ubiquitous phenomenon.
All right, our next question is again from Udemy, and it is, what is the focal length of a plane mirror, flat mirror?
A flat mirror doesn't have a focal length, so the answer is infinite. So a plane mirror is not is reflecting all light at the same angle that it was incident on it, so it's just sort of reflecting at the same angle. To have a focal length, you have to be able to concentrate or gather light, which means you need a curved surface of some kind. So the formal and simple answer to the question is it's infinite.
All right, our next question is about the Mars Curiosity rover. There has been news recently that there are holes appearing in the wheels. Could you talk about what the implications are for the mission and what the causes are?
Yeah, this is there's some amazing pictures of this on the internet. It's a real concern. Basically, in the last few weeks, since this discovery a month or so ago, they have slowed Curiosity's progress by a factor of 2. Their Curiosity is going very slowly right now, and it's sort of picking its way across the Martian surface to avoid any rocks, bigger than this size. They're just trying not to roll over big rocks if at all possible. Well, this was a surprise. You might have argued, shouldn't they have been able to anticipate this? Well, first of all, why does it happen? And why did it happen to Curiosity when it didn't seem to happen to Spirit and Opportunity, the previous Mars rovers? The simple answer is that Curiosity is a much bigger beast. Spirit and Opportunity are the size of go-karts. Curiosity is the size of an SUV. And it's, even though Mars gravity is a quarter, it's heavy. So Curiosity is putting a lot of stress on its wheels. And to say, so the Spirit and Opportunity wheels were smaller, and actually they were sturdier, and they didn't really take any significant damage over the long history of those missions. Curiosity's wheels, as you can see just looking at the images of the holes in them, are really thin, sort of thin-rimmed and thin-edged wheels, and they're made of a very stiff but slightly brittle alloy. I guess it has titanium, aluminum, and I'm not sure all the ingredients. And they were trying to save weight, of course. It's already a heavy vehicle, so it puts a lot of stress on those wheels, especially if they roll over a sharp rock. And Mars, because of the lack of erosion and the lack of an atmosphere, it has really kind of sharp rocks. So it's sort of a conspiracy of the fact that Curiosity is heavy. They tried to save weight by making the wheels light and very thin and out of essentially a strong, brittle alloy. And Mars rocks are really sharp. And so, you still could say they might have anticipated this, so it shouldn't come as a surprise. But they started noticing holes in the wheels. These rocks were just punching holes in the wheels. And, there's nothing they can really do about it now because the mission is there. They can't put Band-Aids or pads on the wheels. They're not able to do things on the fly. So they're just going to have to be extremely cautious about how they navigate. Now they do have good cameras, so they can take paths that avoid further damage, and I think they've decided they're just going to have to do that. It means that Curiosity's progress is going to be slower than anticipated, but hopefully it doesn't, threaten the mission at all. And the number of holes that have been seen on the wheels, I think one of the wheels actually has a number of holes that are very much making people nervous. But if they sort of stabilize the damage at this level and are very careful from here on, it shouldn't be a problem.
All right, our next question is from Wendy. Is there such a thing as a mini black hole, and what are the smallest black holes that have ever been found?
Yeah, good question. Interesting question, because we don't know. Nature makes, as far as we know now, nature makes black holes with a range of about 1 billion in mass. So the lowest mass black holes we see are the natural endpoints of massive stars, where the stellar core is more than 3.5 times the mass of the Sun. All of our stellar mass black hole candidates are in that category. So from the theory of dying stars, 3.5 is the smallest mass black hole you could get. And up at the high end, at the center of galaxies, we have black holes in our galaxy that is 4 million times the mass of the Sun. And the biggest black holes in the center of giant elliptical galaxies are maybe 5 billion, and then there's one that's claimed to be 10 billion times the mass of the Sun. So there's your range of a factor of 1 billion, going up from a few times the mass of the Sun. So what about going down? Well, we don't know of a natural way for nature to make black holes smaller than 3.5 times the mass of the Sun, but that doesn't at all mean they couldn't exist. If some evil alien genius empire managed to squash the Earth overnight, killing us all, of course, but let's ignore that part for a minute. If you could take the Earth and squeeze it to about this size, 2 centimeters, golf ball size, then formally the Earth would fit the definition of a black hole. That would be enough mass density for light not to be able to escape. So formally and technically and in theory, you can have a black hole of any mass. We've just never seen black holes of Earth mass, which would be black holes this big. And we don't know a way for the universe to make such black holes. The question may be motivated by something that's been speculated in the early universe, where possibly, in the early universe, when the density was very high, getting to almost black hole-like, the intense pressure on very small scales could have created miniature black holes. And now by that I mean black holes, instead of the mass of the Earth, are mass like kilograms or grams or something like that. And those black holes of that mass would be the size of subatomic particles, actually. If you took a sort of potato and wanted to make it a black hole, you'd make it smaller than a proton. So in some cosmologies, the very, very early universe possibly could form a froth, because there's no structure yet, so these things would be sort of chaotically and randomly distributed, of miniaturized black holes, just because of the phenomenal gravity of the early universe. It's extremely hard to test that hypothesis. So it is a hypothesis that emerges from some Big Bang theories. And what would happen to such miniaturized black holes, mini black holes? In the theory of black holes, Stephen Hawking talks about the radiation from a black hole, and that leads to black hole evaporation. And evaporation proceeds slower according to how massive the black hole is. The more massive the black hole, the slower it evaporates. So the big black holes the mass of the sun or more are going to evaporate on phenomenal timescales of 10 to the 70 years, something like that. But a micro black hole, a miniaturized black hole that's only a gram and smaller than a proton, actually would fizz away or evaporate on a timescale of a fraction of a second. And that, of course, would put radiation back into the universe on that timescale. And that, of course, would be the signature by which you might hope to detect this phase of miniature black holes in the early universe. So that's, in very simple terms, the possibility out of cosmology in early universe, where you might have a sea of mini black holes, but nobody's observed the signature, and it's not even clear that it's observable in principle. And it's also, the theory is not so sophisticated as to make a unique prediction, I think. So nature can make any size black hole at once. We just haven't found any in this universe that are smaller than 2 times the mass of the sun.
James asks, we've spent a lot of time over the past few months using open data from astronomical sources to build cool products. However, we find the process frustrating, fragmented, and lacking compatibility. What are your thoughts on the current state of astronomical data processing and how they affect?
Yeah, I mean, that's a good question. That's a can of worms, and that's, in my profession, we sort of live with this all the time. I think the problem, well, the real problem is that research astronomy is not sort of driven by market forces very well. It's driven by sort of history, and it's driven by innovators who often invent their own tools, methods, products, software, instruments, and so on. And so the entrepreneurial history of astronomy from innovators, whether it's software or hardware, tends to lead to incompatible things. You know, standards are not uniform, and that is true for hardware as well as for data and software. And so we've sort of grown up with that. Every now and then, and pretty much every decade or so, the international governing bodies like the International Astronomical Union or the American Astronomical Society in this country try and standardize things. And so there are some standardized protocols. There's the, as you probably know, asking the question implies that you have a significant background. There's what's called the FITS standard, and that was developed in, I think, the late 1970s as the standard protocol for data, for packaging data, whether it's spectroscopy or imaging. It's a flexible image transport system, I guess. And that's been used by the national observatories and is propagated to many private observatories. And it's kind of archaic now. It's actually a very archaic standard, but it is still a standard. So there are some data standards, but we're still in a, and there was a sign for a while that the astronomy community, the research and education communities, were going to go in the direction of Linux and Unix and open source and much more open source software and intercompatible software. But that hasn't really happened, unfortunately. There was a hope of that, and some part of the community very much went open source and used the kind of standards that would pertain in the computer industry. But you don't see that. You still see new software being built, new telescopes being built with their own software systems, and they don't talk to each other, and it's kind of a pain. NASA and the space agencies have had to solve this problem because, you know, they have to have interoperable software systems, and they can't afford the expense of supporting many different protocols and standards. So within the space industry and NASA, there are some interoperable standards. But out there in the astronomy research community, it's chaotic, as you know, because you asked the question.
Tonight, another student from UME asks, how are black holes detected?
So, having just talked a bit about the black holes at the two ends of the range, they're detected in different ways. So the black holes that are left over when a massive star dies, if they were just sitting isolated in space, almost by their definition, they would be black, invisible, impossible to detect. You can only detect a black hole by its interactions with something else, either by the fact that it's consuming material and emitting radiation as that material falls in. Remember, nothing leaves the black hole event horizon, but on its way in, by the intense gravity of the attraction of the black hole, matter is accelerated, and that leads to radiation. So when a black hole radiates, it's because of the stuff that's falling in before it gets to the event horizon. So an isolated black hole, truly isolated in deep space vacuum, you wouldn't see it. All the black hole candidates we have come from binary systems. Now that's pretty likely eventuality, since we know that more than half of all stars are in multiple systems, binary, triple, quadruple, whatever. So it should give us a good handle on black holes. There's 40 to 50 good candidate systems where there's a visible star, a star whose age and mass and luminosity you can measure easily. It's the one you see with your telescope. And you know from Doppler shift and orbital monitoring that it is orbiting something that you don't see, an unseen companion. And so you use Kepler's laws in a very simple way, and if the orbital determination implies that the unseen companion is more than 3.5 times the mass of the Sun, that magic number derived by Chandrasekhar in the 1930s, then it must be a black hole. So that's basically the evidence you need to have a good candidate black hole. Additional evidence comes because, as I mentioned, material that falls into the black hole, and it can easily get material from its companion star in a binary system, accelerates and gets very hot. And that actually, for a black hole, means that it emits X-rays or UV radiation, because it gets to temperatures of hundreds of thousands or even millions of degrees. And the temperature, the radiation associated with that temperature is X-rays. So the secondary evidence for black holes, apart from the orbit in the binary system, is the presence of very intense X-ray emission from this binary system. And since the normal massive star or evolved star that you see with your telescope can't be emitting that kind of X-rays, it must come from the vicinity of the dark companion. And that's consistent with the black hole. The supporting evidence. That's the stellar mass black hole. Up at the big end, for the black holes in our galaxy and all the other galaxies that we've found so far, the evidence comes from the influence of the black hole on its environment nearby. So these are black holes at the center of galaxies. The density of stars in the center of any galaxy is hundreds to thousands of times more than in the periphery. So the density of stars in the neighborhood of the Sun is quite low, maybe about 1 star per cubic light year or cubic parsec. In the center of our galaxy, the density is thousands of stars per cubic light year. So the stars are very tightly packed. And they're moving very fast. But they're moving faster than can be explained just by having a lot of stars in one region of space orbiting each other. So the evidence for black holes in galaxies is based on stellar orbits near the center of a galaxy that are much faster than can possibly be explained just by the number of stars you see in the center of that galaxy. In other words, there must be a dark extra mass driving the stellar motions. That's seen in a beautifully transparent way in the center of our galaxy, where we actually map the motions in the orbits of those individual stars, and the course material on Udemy includes beautiful evidence like that. In more distant galaxies, it's a little more indirect. We basically make one measurement with a spectrograph of the nucleus of another galaxy and use the velocity range of stars in that nucleus, so it's just one number, to infer the presence of a black hole. But it's pretty stark evidence. You really can't explain those velocities any other way. So people are fairly confident that those black holes exist. But you should recognize that that evidence is a little indirect, it's not nearly as good as the evidence for the Milky Way black hole, for instance.
Okay, our sort of final question, I think, here will be, I saw in the news that the Rosetta mission reached the comet. Can you talk about the purpose of this mission and science goals and what we hope to learn?
Yeah, that's a great question to finish with, because Rosetta is the big, it's really the big story in astronomy and space in the last few weeks. Rosetta is a mission from the European Space Agency. It was 12 years in the planning and execution, and most people just forgot about it because the mission had to do one of these looping gravitational assist trajectories that took it around the Earth, took it around Mars, gave it a little boost, got it into the right place to approach this this fairly small object in the outer solar system. So this mission, which had to be sort of went into stasis, or they powered it down to save batteries and fuel, and they had to revive it. That was a very nerve-wracking moment for ESA last year to revive the mission, actually no, earlier this year, as it approached its target. It's traveled for over 1 billion miles and over a decade to get to its target. And when it, a week or so ago, made its rendezvous with the comet, which is to say fully matched the comet trajectory and speed, just tracking it, that was a huge milestone in the history of space exploration, because that's the first time we've ever rendezvoused with a comet. We've had close flybys, and we've had missions that have definitely approached comets, and Stardust, of course, flew through comet tail and gathered some of that debris and brought it back to the Earth. That was another incredible mission. But Rosetta is doing something even more ambitious. It's rendezvoused with this comet, and it's basically going to track this comet over the next couple of months. As it approaches the sun, it's going to release a little lander called Philae, F-P-H-I-L-A-E, Latin word. I can't remember what that stands for. Somebody tell me. It's going to release a lander which will tether itself in the, of course, very weak gravity of this small object, and then watch what happens as solar radiation starts to boil off, what would normally be the tail of a comet. It's composed of these volatile gases that are frozen, like carbon dioxide and water vapor and methane and so on, that are normally frozen and get evaporated off as the comet approaches the sun. So this lander and this mission is going to watch this happen from, not from a distance, but from right on the comet itself. And the lander is going to sample the cometary material, do spectroscopy, do quite detailed analysis, again, never been done before. And this is all going to play out in October and November. It's going to be spectacular. I mean, so you basically, this is just the first phase. The Philae lander is going to be another extraordinary achievement if it works, because that's never been done before. And then the ability to study a comet as it gets active and gets crazy, because we know comets are fairly loosely held together, rocks and frozen gases, so the comet structure will actually change noticeably. I mean, this is going to be a dramatic effect on a comet seen from essentially zero distance. So Rosetta is an incredible mission, actually. So it'll be, capturing headlines heavily in the later part of the year. So that was a great question to bring us to full currency in what's going on in space. And thank you for participating. We'll keep doing this every couple of weeks. And you can join the course and keep asking questions online as well as you can do in between these sessions. Okay, goodbye for now.